Hi guys, I hope everybody has managed to find this video. It's taken me a long time to get things in place so that I can try and continue teaching you guys um, from here. So welcome to my home. This is my workshop, which I have turned into my office. I have a whiteboard here that I've always used to track my jobs. Now I'm going to be using it to teach you, I hope. Um, so Not quite sure how this is all going to play out, but a great deal of what I have left to teach you, I think we can do in this fashion. It's unfortunate that we're not going to get a chance to do any more of the labs. You know what? I will post them on Blackboard. You guys have your breadboards there. We don't have a power supply though, so I'm not sure that that's going to work. We're going to have a chance to go through the theory though, carry on with the math, and we'll see how far we can proceed through this. We'll make it work one way or another. It's kind of not at a bad spot where we've left off because I gave you, or you have available on Blackboard, lots of exercise sheets for these combination circuits. So I hope you've had a chance to be working your way through them. If you get through them all, or if you find the last couple of pages are too complicated, you need to practice some more. There's some options available in the Delmar text as well, some sample questions there to work on. What I want you to do, this is question 6 on the bottom of the first page. I'm not going to kill an entire 20-25 minute video to solve for every number. You have the final numbers on the exercise sheet anyway, so you can confirm your work at the end. What I do want to do is point you in the right direction. We'll get through a couple of steps together because very often figuring out where to start is the hard part. Okay, so again, if you're not taking the time to do this on every one, I would suggest you draw it out, put your variables in place, give yourself a chance to see the opportunities that are there, because that's really what we're trying to do. Is we're trying to recognize where we can go. Okay, what blank we can fill in next, so to speak. Okay, there's a few rules. We have 3 rules about a series circuit, 3 rules about a parallel circuit, Kirchhoff's laws. Those are really the things that we're looking at in order to try to solve the problem. Okay, so the first thing I want you to look at when you look at this circuit is try to find trends. Okay, so the first thing that I notice is we have 4 resistors right there that are connected in series. Okay, doesn't matter what else is going on in the circuit, there are 4 resistors connected in series. Okay, something else that I notice is right here, the first resistor is perfectly in parallel with the power supply. So we have a parallel relationship happening there. Okay, these are sort of in series, but there's a node here, so that includes this. So we can't apply any series rules there. Okay, and I've mentioned this before, so I'll say it here as well, and I've kind of done it already, is the strategy is to get as far away from the power supply as we can and work our way back. Okay, certainly I skipped question 6 because question 6, while it's a fairly complicated circuit, it gives us all of the resistances and nothing else. Okay, and so you're forced to start out here, simplify the circuit, work your way back until you have nothing but just a series circuit or just a parallel circuit, whatever it ends up simplifying to. This one's a little more interesting because we do have some variables that are tossed out here and there. For example, so here's where we have to find the trends. So let's start here. We see that we have 4 resistors in series. Well, how do we use that to our advantage? Well, what is it about a series connection that's constant, that we know that they're all going to be the same? Okay, when they're connected in series, that's the current, right? The current is constant through a series circuit. Whether I were to put my meter in the circuit here, or put my meter in the circuit here, or put my meter in the circuit here, I'm going to get the same answer. Okay, whatever current is flowing through this wire must flow through this entire path. Okay, so now I look at my variables, and I've been told the current that's flowing through R5. Okay, so I can take that information and I can just put it into all of these other spaces. So I4 will also be 4 amps. And 4 amps here for I6, 4 amps, so that is the current through R6, and through R7 is also 4 amps. So there we go. That really helps us out, because any place that we have another value, we can use Ohm's law to calculate the third value. So that really comes in handy. All right, filled in a lot of blanks for us very quickly. Okay, now that's going to allow us to probably finish this off, possibly. I'm not quite sure. Like I say, I'm not going to go through the entire exercise with you and calculate every number. But one other thing that I see, I mentioned that R1 is perfectly in parallel with the power supply. So what is it that's constant in a parallel circuit? It's the voltage, right? So whatever voltage we have at the power supply, that's going to be the voltage drop here across our first resistor. So there's two different ways to state this to say the same thing. One is the rule of a parallel circuit is that each parallel branch is going to see the same voltage. Okay. The other thing is to apply Kirchhoff's voltage law here in this closed loop. So we have a voltage rise of 220. We will have a voltage drop of 220 also. Okay, so stating it either way gives us the same result. This parallel branch is 220. Okay, so something else that I see, and this isn't going to get us a number yet, but just understanding some of the theory and some of the logic, is there's also a complete loop right there where we can apply Kirchhoff's voltage law. Okay, so now this is our voltage rise of 220, and the voltage drop will be E3 and E2. So these two numbers, okay, and if we knew one of these, that would be great. We could find the other, but we don't know either of them, so it's not really helpful yet in terms of getting a number. But in terms of understanding where we have to get to and checking our work when we start filling in some numbers, we know that E2 plus E3 will have to equal E1, okay, because there's the loop. So let's see, when we go through this, we're going to be able to find E7, we're going to be able to find E6, we're going to be able to find E4, we don't know E5, so we know 3 of our 4 voltage drops. Okay, in this loop over here, E3 is going to be our voltage rise. So again, we can figure out where our numbers are going to end up, but we don't know what those numbers are going to be. So we don't know how the voltage splits here, and then we don't know how it splits there. So now the question becomes, where do we go next? Well, let me see. Where can we go next? Well, we've got all these currents, right? So do we have any other currents? Well, I see a current here through R2. I know that this is 7 amps. So I feel like we can probably apply Kirchhoff's current law to this node right here. Okay, so current's going around the circuit in this direction. Okay, we solve our circuit in a clockwise direction. If we went counterclockwise, we could get all the same numbers, but we can't mix and match. We've got to make a decision. So we've always typically gone around clockwise, so let's carry on. What that means is that this 4 amps is going through the circuit clockwise, which means it's entering that point right there. Okay. It also means that current is exiting that point right there. Okay. And finally, there's going to be current coming down and entering the point through there. Okay. So there's our current flowing through our circuit in a clockwise direction. Now, do we know numbers? We sure do. We have 4 amps entering the node here from the right, and we have 7 amps exiting the node here to the left. Okay, so even if we couldn't figure out this arrow, now we know what it must be. Okay, if there's 4 amps entering and 7 amps exiting, there must be an additional 3 amps entering from above. So I3 must be 3 amps. Okay, so is that a useful piece of information? Well, once again, it's one step closer. Okay, let me see. I wonder where we should go next. Huh. Tricky. Without filling in the rest of these numbers, maybe we should do that. 7 amps. Because we don't know the current here, do we? Oh, sure we do. Oh, absolutely we do. Oh, yeah. What's this current? Okay, so if I equals E divided by R, and E is 220 volts, then R is 10 ohms, which means, wow, there's 22 amps there. So let's do Kirchhoff's current law one more time. Right here, we have 7 amps entering from the right. We have 22 amps coming down from this branch above, and therefore exiting the node to the left will be the sum of those two, which is 29 amps, which means up here IT is 29 amps, which is now going to allow us to find RT. Okay, and I believe that should allow us to fill in whatever blanks we have left. There's only a couple. Okay, I told you I wasn't going to do the entire question, so I think I will leave it there and allow you to finish it off. Okay, thanks guys. Welcome to our new teaching environment. I will provide probably a couple more of these over the next couple of days, and I believe we're ready for a test next week. So the test will go on Blackboard. Okay, you guys will need to log on to Blackboard and do the test. I'm going to post it for a full day, I think even into the evening. I don't know what you guys are doing right now. Are you still working, or are you all sitting at home isolated like I am? There's a discussion board set up on Blackboard. If somebody, a couple of you would like to just throw a message my way, let me know what's happening in your world, or send me an email. But let's plan on, I'm going to say, middle to late next week, so either Wednesday or Thursday, which is about a week from now. I think we're going to be ready to do some testing on this material. Okay, so more to come on that later. I'm going to shut it down there. More to come.